Good afternoon, everyone. I'm very glad to have the opportunity to present this work that has been the result of a collaboration within a group sponsored by ESA on the SWARM mission. Okay, so to start with, I must define a time scale that is important to understand the core dynamics that we put forward from the analysis of torsional waves that we have deciphered from magnetic data some years ago. This is the alpha time. Typically, this time, which is the magnetic time in the core when you distort magnetic field line, is typically a couple of years. And this time was the way we proposed the first picture of the magnetic field, the strength inside the core of a few millitesla. And this few millitesla is much larger than the field itself that we witness at the core mantle boundary. Another point that is important is associated with this time, the time for the propagation of alpha waves. We have a velocity, which is the velocity of these waves, that is much larger than the fluid velocity inside the core. Typically 10 to 20 kilometers per year for the fluid in the core, to be compared with 1,000 kilometers per year for the propagation of these waves. So now, with all these series of satellite missions, starting from Ørsted, CHAMP, SWARM, and now the MSS mission, we are able to build this kind of picture. This is a work by Magnus Hammer, where we show the secular variation here at many points in space called virtual observatories. What we witness are fluctuation of the secular variation, the rate of change of the magnetic field, of the order of 10 nanotesla per year. So we knew this already from observatories, but now we are able to witness that all over the world. And what we see is, especially in the equatorial belt, that we have these recurring patterns. It is not possible to explain these patterns only based on zonal motion, and these must be non-zonal, so we knew that, but so far we had no deterministic understanding, physical understanding of these. We benefit now also of some huge improvement in the capacity of reproducing with computers the dynamics in the core. I show here some illustration from simulation by Julien Aubert in Paris, where we see here isolated what we call quasi-geostrophic, that means almost invariant along the axis of rotation, alpha waves that are propagating along these orange magnetic lines. So this axial invariance, it comes from the dominating Coriolis force. And in the simulation, the propagation of these MHD waves is actually what is exciting the jerks, the rapid fluctuation that are seen in the secular variation. So this is an illustration, again, taken from a simulation by Julien Aubert, where we see jerk everywhere, excited by waves in the core. So some years ago, there was a whole playground of waves that are available to play with in the core. So you have the Coriolis force, you have the magnetic force, and among all these waves, you have what we call the magneto-Coriolis modes. And these waves, they are very dispersive. And they were believed, these waves, to be undetectable at periods close to the alpha time, because their length scale would be too short to be accessible. So that was the picture we had in mind. And actually, I show here a spectrogram, it's some work by Felix Gehrig, of some waves in an eigensolver. So on the x-axis, you've got the frequency. On the y-axis, you've got the ratio of kinetic to magnetic energy. And you've got either very kinetic waves. These are inertial waves, like the one you mentioned earlier on. You've got here equipartitioned. This little point here are torsional alpha waves. So alpha waves show equipartition of the magnetic and kinetic energy. And on the bottom left, you've got the MC waves, the slow MC waves. And actually, there exist some waves, MC waves, that have a period that is close to that of alpha waves. And this is an illustration here, taken from some work by Felix. Here you have the surface magnetic field and the surface azimuthal flow. in a dimensionless unit. And what is very interesting is that actually these are very large scales in phi, okay? So low wave number phi and a relatively high wave number in the S direction. And actually these are detectable for a geometrical reason. And the geometrical reason is that if those motions are quasi-isotrophic, that is aligned with the invariant along the rotation axis, then a very small length scale in the S direction close to the equator project into a relatively broad length scale in theta. And that's what makes them observable from magnetic data. So based on this improved simulation, improved understanding, and improved data, we have tried to put all this into a data simulation tool called the PyGeodin. It's typically taking statistics in space and time from geodynamo simulation and make an analysis of magnetic data based on this knowledge. It's capable of assimilating data from satellite, ground-based data in form of virtual observatories, ground observatory, or ghost coefficients. So what we found is this kind of motions. On the top left, you've got a latitude time diagram over the satellite era. And you see that the motion that we observe, responsible for the fluctuation in the secular variation, are essentially concentrated near the equator here, with a period of about 7 years. And when you look on this bottom diagram, you see the time longitude plot, so you see a westward propagation of these patterns. The speed is very strong, I mean, very large, typically 1,000 or more kilometers per year in the phi direction and a few hundred kilometers per year in the S direction. So in both cases, much larger than the fluid flow, here a few kilometers per year. The shape of these waves look like this. So you can see they are centered in the equatorial belt. That's where they are the stronger, and that's where also the magnetic signal is the largest. So these results have since been confirmed by several independent analyses, for instance, by Guillaume Ropp and Vincent Le Sur or Cathy Weller. So now we have been able to isolate these waves, but I believe there are such waves on a broad range of timescales, because there is no reason it should not be the case. And actually, this wave is not the fundamental clone of the MC waves. I show here a power spectrum for the 3 components of the magnetic field at Hermanus in South Africa. And you can see on the Y component, which is the cleanest in green here, that you've got actually this peak, which is the 7-year peak, that maps into the flow waves that I've shown before. But you have also a peak here at 15 years and another one at 3.5 years or so. And when you look at the spectrogram of the flow models that we are able to produce, you see here the 7-year period is there. You've got the South Pole, the North Pole here, the equator. So this magnetic signal, it projects into the flow models in this way. And you see as well signals at 15-year period and something like 3 to 4 year period. So I would bet that these are other MC waves that we are able to witness with magnetic data. For me, what this picture tells us is that we really need, there is a real interest in having long time series from space, because from this we will be able to have a family of waves, not a single wave. Okay, and with a family of waves, we can start to probe the Earth, either deep in the core or possibly in the mantle as well. So another interest in future research is what I will try to describe here. What I show here is the power spectrum of some flow coefficient from a dynamo simulation by Julien Aubert. The gray one is the 71p dynamo. It's at an Ekman number 3 times 10 to the minus 10. It's large in simulation. And the black one is another of his family of dynamo at 310 to the minus 12 Ekman number. And you can see that as you decrease the Ekman number, you excite shorter and shorter time scale. But what you see also is that there is a cutoff frequency here between where the spectrum broadly follows the -2 slope and here -6. It's pushed toward short periods. Okay, so we have not been able to witness the physics that is occurring here. And you see this cutoff frequency, it is associated with the alpha time, which is shown with these dotted vertical lines here. So you push, as you go towards the Earth's core, you push the cutoff frequency towards the right, and the physics we are able to witness is somewhere here. There is some interest in looking at this cutoff frequency, which is function of diffusion and also function of the alpha time in the core. But diffusion where? We don't really know. We don't have a deep understanding of this. It could be diffusion close to the boundary, or it could be diffusion in the core, deeper. But if we are able to go to shorter time scale with low inclination orbit data, like the MSS mission, we might also be able to have a better understanding of the mantle conductivity. I refer here to some work of a PhD student in Grenoble, together with Nicolas Gillet, where we show that the core sees the mantle as an insulator on long periods, whereas it sees it as a conductor if there is some conducting layer on short periods. So going to shorter period, it is a way to probe the deep mantle from the core dynamics. So I finish here. I think the discovery of this wave, it builds a possibility to probe the deep Earth in many senses. So first to probe the dynamo field, because these waves, they are carried by the dynamo field, but also to probe physical properties like the possible stratification below the core mantle boundary, or the deep mantle electrical conductivity. It might be also a way, if we have a good enough a model of the background field in the core, to have some prediction of the magnetic field. So this really motivates long-lived multi-satellite coverage from space. And I stop here. Thank you.